Right, so let's get started. My name is Indaba𝕏. I'm a lecturer at the University of Cape Town. So today I'll be talking about work that was mostly done while I was a postdoc at the University of Washington, and this work has been accepted as a paper for this year's ICLEA. Right. So there has been substantial advances in the field of natural language processing in recent years, both in natural language understanding tasks, such as question answering, and in natural language generation tasks, such as machine translation or summarization. These advances were driven by deep learning, and more particularly by large pre-trained models. These models were trained on objective functions based on the task of language modeling, which is estimating the probability of a sequence of words. The representations that deep learning models can learn through language modeling training have been shown to be very informative for improving language understanding when applied to different language processing tasks. The language modeling probability can be decomposed into the probability of predicting each word given all the words preceding it. So we can imagine generating each word in a piece of text, one at a time, from left to right, based on the probability distribution over possible words. Deep learning-based sequence models, such as LSTM recurrent neural networks and transformers, have been shown to be very successful at language modeling, as they are able to learn better contextual representations and model long-distance dependencies much better than previous approaches. One direct application of a language model is when you are typing on your phone, and the system is making suggestions for the next word you might want to type. But language models are now powerful enough that they can be used to generate paragraphs or documents, not just to predict the next word. So the task that we are studying in this work is how to generate a text passage which is a plausible continuation of a prompt which is given, which is the start of a document. Last year, OpenAI released a large neural language model called GPT-2. This model received a lot of attention because of the high-quality text passages it is able to generate. In this example, the model is given a prompt, which is the start of a made-up newspaper article about unicorns living in the Andes Mountains. The model was able to generate a very convincing-looking continuation of this prompt, making up details about the unicorn's appearance and how they were discovered in perfectly fluent text. However, the question of how to decode text out of a language model turns out to be not as straightforward as one might think. In this work, we review different strategies that have been used for language modeling and decoding. Then we will identify why they often fail to generate coherent text, and we will propose a new method called Nucleus Sampling, which mitigates these deficiencies. In our experiments, we used a large version of GPT-2, which is a transformer-based language model trained on 40 gigabytes of text. We generate text passages of up to 200 tokens each, conditioned on the initial paragraphs of documents in the web text validation corpus. And then we will perform various analysis and evaluations of these generations. The decoding strategies that we will consider fall under three categories: maximization-based decoding, sampling-based decoding, and truncated sampling. We will introduce each of these decoding methods in turn, discussing their advantages and disadvantages. The first approach to text generation is to aim to maximize output probability. If we assume that we have a good model, that seems like a sensible thing to do, as the model should assign higher probability to higher quality text passages. It is untractable to find the global argmax output according to the transformer language model, so we have to approximate maximization. One approach is through greedy decoding, that is, picking the highest probability word at each time step and generating the words one at a time. The other strategy for maximization-based decoding is beam search, which involves maintaining a short list of the highest scoring partial generations at each time step. Beam search is a standard decoding method for tasks such as neural machine translation, summarization, and data-to-text generation. However, for our generation task, maximization-based decoding turns out to generate degenerate text. Using the same prompt as in the OpenAI example, beam search generates output that tends to be very generic and repetitive. And there isn't much difference between beam search and greedy decoding in this task. As an example with a different prompt, we see that the generation using beam search gets stuck in a repetitive loop. And this is something that's quite common for maximization-based decoding. A different decoding strategy is to sample outputs from the language model's probability distribution. The motivation for this is that if the model distribution is a good estimate of the true probability distribution over text, sampling should produce representative outputs. However, we see that sampling also produces degenerate text. While it mostly avoids the repetition and genericness of maximization-based decoding, sampled outputs tend to be incoherent and nonsensical, as can be seen in some of the highlighted phrases in this example. To overcome the weaknesses of generation by peer sampling, a number of modified sampling-based methods have been proposed. The first is sampling with temperature, which modifies the shape of the probability distribution by dividing the logits by a constant before applying the output softmax function. In our case, the temperature is set to give more weight to higher probability words and less weight to lower probability words, that is, to make the distribution more peaked. Sampling with temperature improves generation quality, but the output still exhibits many of the same coherency problems as peer sampling. The challenge here is that if the temperature is set too low, the text again becomes generic and repetitive, similar to maximization-based decoding. A more drastic solution is to perform truncated sampling. Fan et al. Proposed top K sampling, which samples the next word from the K highest scoring probability outputs, and the sampling is then performed based on the relative probabilities of the top K words and effectively setting the probability of all other words to 0. This approach produces better generation quality than sampling with temperature and has been used widely to generate text from language models. Indeed, the generations displaying the high quality output from GPT-2 were generated using this technique. However, generations using top-case sampling can still have some repetitions and incoherencies, as in this example. In this paper, we propose a novel decoding method called Nucleus Sampling. Instead of sampling from the top k words, we sample from the set of words containing the top p proportion of the probability mass. So if p is 0.9, we will sample from the set of words containing 90% of the probability mass. The set of words being sampled from is called the nucleus, as it is a relatively small set of words containing most of the probability mass. Here are the equations for defining the top p vocabulary, which is the set of words being sampled from, and also for renormalizing the probability distribution after setting all other words' probabilities to 0. The intuition behind nucleus sampling is that the number of plausible next words to generate varies widely depending on the context. For some contexts, there are only a few reasonable next words, and the probability distribution is very peaked. But in other contexts, there can be a large number of plausible next words, and the distribution is more flat. Methods such as top-case sampling are unable to capture this intuition, and sampling from a fixed-sized short list of words will never be able to include all the plausible words and exclude all the implausible ones. Qualitatively, we see that text generated by nucleus sampling has longer coherence than that of other truncated sampling strategies, due to better control over which words may be generated. And despite these advances, the generation still isn't perfect, and especially for long generation, there are still some issues. Now that we have discussed the various language modeling decoding methods and motivated nucleus sampling, I proposed new decoding method, we turn to the question of how to evaluate text generated by these methods quantitatively. This is a challenging problem, as most of the existing evaluation metrics for text generation have limitations. We propose a set of evaluation criteria that together enable us to compare the output of the decoding algorithms along various dimensions. Our first evaluation is perplexity, which is a normalized measure of the probability that the model assigns to text passages. Perplexity is the standard metric for evaluating the quality of language models. We use perplexity to compare the quality of text generated by the various decoding algorithms to that of human written text. In this evaluation, the closer the perplexity of generated text is to human written text, the better the quality of the generated text. The results show that nucleus sampling and top-case sampling generations are closest to that of human text. Notable in these results is the very low perplexity of greedy decoding. This means that the model is assigning a very high probability to the repetitive, nonsensical examples we saw earlier for maximization-based decoding. Sampling also performs worse than truncated sampling, which indicates that sampling words from the low probability tail of the distribution causes the overall probability of generated sequences to become worse than it should be. Using nucleus sampling, it is possible to calibrate the value of p, so to set it in a way that it is matching the perplexity of human text. And empirically we find that that produces the highest quality output. Next we measure the diversity of generated text. Self-BLEU, which is a measure of how much overlap there is in the vocabulary usage between different outputs of the same model. A low Self-BLEU score indicates more diversity. In our case, the goal again is to match the diversity of human written text, as there are also disadvantages in generating text that is too diverse. In this evaluation, we see that truncated sampling methods again perform best, so they are closest to the human examples we are comparing against. We also measure diversity in terms of the distribution over vocabulary usage for different models. Now I'm not going to go into details of that here, but the results are similar than for Self-BLEU. Finally, we measure repetition, and in particular the probability that the output will get stuck in a repetitive loop, repeating the same phrase over and over again. This quantifies the maximization-based decoding is extremely repetitive, as in the results it ends up in a loop for about almost 75% of the time, while sampling-based generations are very close to the human distribution in terms of a very low probability of occurrence of this repetitive loop. So while the automatic evaluation metrics we have used so far are very useful, they cannot directly assess the coherence of the generated text, or give an overall assessment of quality. Therefore we turn to human evaluation. While humans can evaluate the coherence of text, it is hard for them to assess diversity across generations. So, to combine the strengths of human evaluation of the quality of text and machine automatic evaluation of diversity, we use an approach called Human Unified with Statistical Evaluation, or USE, which was proposed by Hashimoto et al. In 2019. USE uses human judgments of generation quality together with language modeling scores as features in classifier to distinguish human written and machine generated text. The better the system, the harder this discrimination task should be. The caveat of this evaluation is that for truncated sampling, we need to interpolate the truncated distribution with the original distribution to get valid USE scores, otherwise there are some zero probabilities. The results show that nucleus sampling performs best overall, followed closely by top K sampling when a large value of K is used. And other decoding methods perform substantially worse. And it's also notable that while top K sampling has been used before, it was mostly used with smaller values of K, which are scored lower according to our evaluation criteria. So, in conclusion, our analysis shows that the probability distribution of large language models, such as GPT-2, are systematically wrong in ways which degrades language generation quality. The truncated sampling can address these problems by not sampling from the unreliable tail of the probability distribution. And in this work we introduced nucleus sampling as a principled and well-behaved decoding method for improving generation quality. Right. So thank you for listening, and if you have questions you can leave them in the live chat or in the comments, or get in touch with me via email. So thank you very much.